In this part, we'll look at reward shaping. The problem with some methods such as Monte Carlo tree search and model-free methods is that they spend a lot of time at the start searching for rewards and they don't know where they are. This is known as the cold start problem. Effectively, they're taking a lot of random actions until they reach a reward to give them some signal. Reward shaping allows us to give those algorithms a small fake reward that sort of nudge them in the direction of good actions towards rewards. We'll look at how to define shape rewards in a systematic framework that gives us nice theoretical guarantees. And then we'll look at an example that examines the effect of reward shaping. We'll also look at a related technique known as Q-function initialisation, which is shown to be very similar to reward shaping, but works in a slightly different way. By the end of this part, you're expected to be able to do the following learning outcomes. Explain how reward shaping can be used to help model-free and simulation-based reinforcement learning methods to converge. Manually apply reward shaping to a given potential function to solve small-scale MDP problems. Design and implement potential functions to solve medium-scale MDPs automatically. And compare and contrast reward shaping to Q-function initialization. Let's get started. So now let's look at the problem the reward shaping aims to mitigate. We see here again the freeway example in which we have to get the kangaroo from one side of the road to the other. The problem is it was never able to successfully navigate to the other side of the road because it spent too much time exploring short-term options and was never able to get to the other side in order to get a good reward. This is known as the cold start problem. There's just simply no information to go on. However, if we could give a small nudge to this algorithm, that is, encourage certain actions over others, we might be able to help it get to the other side of the road. That's what reward shaping aims to do. So basically what this means, if you're using Monte Carlo tree search or model-free reinforcement learning, at the start our Q function, which is arbitrary, has no information to go on in order to tell this particular algorithm that going up many times is what's needed to get to the other side of the road. The likelihood of selecting enough up actions and few enough down actions in order to get to the other side of the road is so small that this algorithm never gets to the other side of the road and never gets that signal. It's not just MCTS that this happens with as well. There are other videos you can watch of reinforcement learning algorithms playing freeway, and it takes perhaps several hours to get to the other side of the road even once to get that initial signal. Once it grabs onto that signal, it's able to exploit it a little bit, but how can we encourage it to get that signal a bit earlier in learning? So what is reward shaping? Well, the basic idea is to shape the rewards by giving out small, fake, intermediate rewards that nudge the algorithm towards the real rewards more quickly. This helps avoid the cold start problem. So in many applications, we'll have some idea of what a good solution might look like, or at least we'll have some information that allow us to give the algorithm some indication of what differentiates good moves from bad moves. So can we nudge our algorithm towards more promising solutions early on? So we can give domain knowledge, that is information about the domain that the human modeler knows about the problem, to the algorithm in order to solve this. What would be a good nudge for the freeway example that we see here? Well, we know that the problem is to get to the other side of the road without being hit by a car, and we know that it's already quite good at not being hit by cars. So what we could do is give a small intermediate reward for moving up rather than moving left, right, or down. This very small intermediate move would encourage the algorithm just to go up a little bit more than it would in other directions, and it might help it to reach the other side earlier. So let's define the idea of reward shaping a bit more formally now. First, let's look at the idea of updating in Q-learning again. In Q-learning, we want to update the value Q S of A after we execute action A in state S and observe the reward in new state. The updated value looks like this. The old value plus an expression that's multiplied by our learning rate, the reward plus the future discounted reward minus the old action. I've left a bit of a gap here to help us out. In reward shaping, the idea here is that we provide a small fake reward, which we're going to define as F SS prime for transitioning from state S to state S prime. So in other words, if we can provide a function that says if we go from S to S prime, that's either positive or negative, then we can provide a small bit of feedback to our learning algorithm as to whether this is good behavior or not. Our function f is defined over these states. If this expression here is negative, then we discourage choosing action A in state S. If it's positive, we encourage it. We call this expression here the shaped reward. The idea here now is that for this small bit of fake reward that we get here, we're feeding back to our Q-learning algorithm that going from state S to S prime is positive, therefore choosing action A in state S would be positive. So for example, in the freeway example, if S was one state and S prime was the state above it, we would give a small positive reward, and if S prime was below it, we'd give a small negative reward. This would encourage it to move up rather than backwards or left or right. Potential-based reward shaping is a type of reward shaping that gives us good theoretical guarantees. In potential-based reward shaping, our function f is of this form. Where we call phi the potential function and phi of s the potential of state S. In potential-based reward shaping, instead of defining the function f, we define phi, the potential function. This is a heuristic function that allows us to estimate a value for each state S. We then, from this, can define the value f S prime by calculating this value here. If we define f like this, in this pattern, using the potential reward function, and we use the reward update from the previous slide or the SASA version of that, this is still guaranteed to converge to the same Q function that it would after an infinite number of samples. A proof of this is in the notes. We won't go into it in this video. However, while it provides guarantees about the end result of convergence, potential-based reward shaping may either increase the amount of time it takes to learn or decrease it. A well-defined potential function will decrease it. However, a poorly defined potential function can increase it. And we won't know until we try and train it. So for that reason, we have to be really careful on how we define our heuristic, make sure it's a good heuristic in order that it will converge more quickly than without it. Now let's look at an example of reward shaping in Q-learning. Here's our familiar Gridworld example here, and we need to define a heuristic function phi, a potential function, in order to guide the agent towards our positive reward up here. What would be a good heuristic function? Well, seeing as this is a navigation along a grid, we might, for example, use the Manhattan distance as a heuristic function. If you're unfamiliar with the Manhattan distance as a heuristic, it's simply the number of squares vertically plus the number of squares horizontally we are away from our goal. Let's define this a bit more formally. It's often a good idea to normalize this by the width and the height as well. To do this, we just divide by where W and H are the width and the height of this respectively. So 4 and 3. So this is our Manhattan function. It looks at the distance between the goal and where we are on the x-axis and the distance of the goal where we are on the y-axis, adds them together and divides by the maximum possible distance of each of those. Let's have a look at applying this to one of the states now. assume that we're in the middle of learning and we're at state 1, 2 here, and we go right. Also assume this is the very first episode of training, so our Q values are all 0. We've initialized them all to 0. Without reward shaping, the update of this would simply be 0. Because there's no immediate reward, because the immediate reward is 0 and the estimated future discount reward is also 0. However, let's look at it with reward shaping. First, let's calculate what our value of f will be. If we successfully go right, we end up in 2, 2. Therefore, our value will be gamma phi 1, 2 which just comes to so the shaped reward is 0.12. This is a small reward that we're giving to the algorithm. Now if we go to do our Q update here, let's look at what will happen. We know that QS of A is 0, the immediate reward we get is 0, our estimated future reward is 0, and this is 0 as well. So the only thing we have to do is take our additional reward, our shape reward, which is 0.12, and multiply it by our gamma, which up here is 0.1. Therefore our update will be 0.12. It will receive this award the first time it ever executes and gets feedback from this state here. But if we do this step for the other actions in that state, we'll also see that they get some shape reward as well. Let's have a look. Shape reward for this one is 0.012. The shape reward for going up, if we calculate it, would be negative 0.06. Shape reward for going down would be the same. And the shape reward for going left would be this would all be given the first time we execute these actions, even if it was on the first episode. This would mean that these values are available to our multi-arm bandit algorithm when it's choosing an action to exploit or explore. If it's choosing to exploit, it's more likely to choose this action that goes to the right here than it is up or down, and they're both more likely than going left. As you can see, this is kind of nudging towards our final goal. However, this isn't always going to work for us. If you consider being down in this bottom right state here, our heuristic is going to tell the algorithm to go up, which is straight into the negative state. However, there are always going to be states where the heuristic is misleading. If we could define a heuristic that's never misleading, then we simply wouldn't need to do reinforcement learning anyway. We could just take the heuristic function and follow it all the way to the goal. So for that reason, our heuristic function is an approximation. There's going to be some situation where it gets it wrong. However, our algorithm is still going to learn going up in this state was a very bad option, and it will wipe out this small heuristic reward that we gave it in with potential reward update. Now let's look at the effect of reward shaping in a version of Gridworld that I call Super Gridworld. Super Gridworld is just a version of Gridworld with a much larger state space. We still start in the bottom left and have to get to the top right, and there's one wall here, but there's a lot more steps in between. On the screen here is the Q function after 1000 episodes using standard Q learning without reward shaping. We can see here by all these numbers, and the actual numbers don't really matter too much if you can't see them, but we can see that most state action pairs have been explored. We can see this, if you can see closely enough, it's because these numbers are non-zero, which is what they're initialized to. If they are 0, I use a slightly different shade in order to indicate that they've never been explored. Now let's have a look at the Q function after 1000 episodes using reward shaping. In this version, these state action pairs haven't been explored simply because they're not required to be. Our Manhattan heuristic nudges the algorithm up and across towards the goal without exploring most of this irrelevant state space. Now, it might not necessarily look the same if I ran this again. We might see instead that it explores this region of the state space or even this region of the state space here. But what we probably would see is that it wouldn't be anywhere near as comprehensive as the vanilla Q learning version, but this reward shape version saves a lot of time not exploring actions that's not required. Although these actions and state action pairs here could be relevant, we already have one good solution, so we don't need to explore many more. Now let's have a look at the effect of this on our training. Here we have a graph that plots the average episode length per episode during training. So we trained both algorithms for 100 episodes, and we measured how long each episode was before it hit a terminal state. We can see here that with tabular Q learning, the early episodes are really quite large as the algorithm doesn't have much of a signal to go on. So it gets stuck in certain states where it doesn't know where to go. Even after it gets some initial signal, it still gets stuck on some of these states. Whereas the reward shaped algorithm, well, it learns pretty much straight away to go directly from the bottom left to the top right using the Manhattan distance heuristic as a potential function. Now this is just one example where the heuristic function basically takes us almost straight towards the goal. However, what it does show is that with a good potential function, early simulations can be much more efficient and save a lot of training time. However, it's important to note that if we designed a poor potential function, this could have the opposite effect. An approach that's related to reward shaping is called Q function initialization. So recall that temporal difference learning methods can start at any arbitrary Q function. And intuitively, the closer it is to the optimal Q function, the quicker it's going to learn, or the quicker it's going to converge. So imagine if we happen to initialize our Q function to the optimal Q function at the start, it would converge in one step. Q function initialization effectively tries to do this. It tries to initialize our Q function to something that's closer to the optimal Q function than all zeros. We can use heuristics such as potential functions to assign higher initial values to better states at the start. So for example, if we think about our earlier example, if we defined Q to just be where S is the state that results from applying action A, then we would have a very good Q function to start off with, provided that our potential function underneath was good. In fact, it turns out if we just define our potential function as our value function and our potential function is static, then reward shaping and Q function initialization are equivalent. They will converge onto the same policy and in the same amount of time. So if we think about this, using this, go back to our example earlier, we might define our initial Q value function like this. From state 1, 2, if we go up, we'll get the potential function reward, negative 0.06, down we'll get the same, right we'll get some positive reward, and left we'll get a strong negative reward here. Now, if we initialize our Q function to those values in this state here, again when our multi-arm bandit chooses an action here, it's more likely to choose that right action than any of the other actions and move towards the goal. In this section, we looked at reward shaping. Reward shaping is giving small fake rewards that are defined using domain knowledge into our learning algorithm so that it can avoid the cold start problem. If we use a special type of reward shaping called potential-based reward shaping, then this is guaranteed to converge in the same way that the underlying algorithm would if we didn't use reward shaping at all. We saw that a well-defined potential function can reduce the length of episodes early in learning and therefore reduce total learning time. And we also discussed Q function initialization, which is a similar technique that's shown to have equivalent outcomes if our potential function is static. The techniques we looked at here can be applied to any of the learning algorithms that we've seen so far, and they can also be applied to some of the algorithms that we'll look at later. So stay tuned.